So what about these particles? We call these subatomic particles because they're smaller than an atom. So all atoms have the same 3 subatomic particles, protons, neutrons, and electrons. There are other particles, muons and gluons and all sorts of things. We're not going to talk about those in general chemistry. This is the 3 big ones. So protons and neutrons have essentially identical masses. For our purposes, they're the same. They differ in the 4th digit here. They're both very small, 10 to the minus 27 kilograms. The mass of the electron is less. It's 10 to the minus 31 kilograms, so significantly smaller, almost 2,000 times smaller. To help you get an idea of the relative sizes, if the proton had the mass of a baseball, an electron would have the mass of a grain of rice. So very small in comparison. So kilogram is obviously not a great unit for expressing the mass of these particles or even the mass of an atom. And so we use another unit called the atomic mass unit. It's a very descriptive name, although not very creative. So the atomic mass unit, abbreviated AMU. The AMU is defined as 1/12 of the mass of a carbon atom that has 6 protons and 6 neutrons. So if 1/12 of that was an atomic mass unit, then that atom with 6 protons and 6 neutrons would weigh 12 atomic mass units. So the mass of a proton or a neutron is approximately 1 atomic mass unit. Yes? Yeah. Students are often, wanting to know, what do we need to memorize? You do not need to memorize these masses. If you needed it for a calculation, you could look it up or it'd be given on an exam. So here's a nice table that summarizes these 3 subatomic particles. So the proton, the neutron, and the electron, here are their masses in kilograms. Here are their masses in atomic mass units. Now this is, giving it very precisely, which sometimes we need, but proton's mass is essentially 1 atomic mass unit. Neutron is 1 atomic mass unit. And an electron is approximately 0. The charges, now the charge on the electron was determined in Millikan's oil drop experiment. The charge of the proton is the same magnitude but opposite in sign. So that when you have 1 proton and 1 electron together, their charges add up to 0. The neutron is neutral and has no charge. And these numbers also are really not very important to chemists. We're more concerned with the relative charge. And so we say, well, the electron has a -1 charge, and the proton would then have a +1 charge, and the neutron is neutral. So this part right here, you should know those. Relative masses, relative charges. It's 1s and 0s. Matter is generally charge neutral because protons and electrons are present in equal numbers. Positive and negative charges are attracted to each other. So when we separate those charges, nature generally brings them back together. The imbalance is equalized often quickly and very dramatically. An example of this is lightning. So lightning occurs when negative charge builds up on the clouds and positive charge builds up on the ground. And this electrical discharge, the lightning that we see, is the re-equalization of those separated charges. Static electric shocks are also an example of this imbalance equalizing. So, you're wearing your socks, You're walking around the house in the winter when the air is really dry, and then, shuffling around, and then you touch a metal door jamb, and there's this little shock, right? Or taking a balloon and rubbing it on your hair, right? You can get static electric shocks because that causes the positive and negative charges to separate, and they don't like to be separated. So the number of protons in the nucleus of an atom is what defines the atom as being a particular element. We call it the atomic number. It's given the symbol Z from the German word Zahl, meaning number, even though it's an atomic number that starts with A. So if we look at helium atoms, here's a helium balloon. We look at these helium atoms. Every single one of these helium atoms has 2 protons in its nucleus. The graphite in your pencil is made of carbon. Every single carbon atom has 6 protons. That's what makes it carbon. I think of protons as being like the personality or the soul of the atom. You can change what you look like on the outside. You can change how you act, but you can't change who you are. You are still yourself, right? So the atoms, outside of nuclear changes, the number of protons is constant. And that is what identifies an element. Mm-hmm. We're going to get to isotopes. Yeah, good question. So here's one version of the periodic table. This periodic table has element symbols and atomic numbers, and this one actually has the names. Generally, we don't use periodic tables with names because the name takes up a lot of space that we need for more information. That's why I gave you a list of element names and symbols to memorize. So here's beryllium. There's its chemical symbol. The number above it is the atomic number, Z. That tells us there are 4 protons in the nucleus of beryllium. So we could look at any of these elements. Here's iodine. Iodine atoms have 53 protons. Any questions? So each element has a name. It has a unique atomic number, and it has a unique chemical symbol because those names get kind of long, and so we have abbreviations. The abbreviations are either 1 letter or 2 letters. The first letter is always capitalized. If there's a second letter, it is never capitalized. So examples, we have the chemical symbol for helium is capital H, lowercase e. Those are the first 2 letters in the name, helium. Carbon has the symbol C. Ca, you might think, well, why can't we use Ca for carbon? Well, Ca is calcium. And so that second letter is used when we have more elements starting with the same letter.
Why do we have like odd ones like Pb is lead, Sn is tin?
That's an excellent question. Why do we have some of these weird ones? How about sodium? That one's a weird one. Na is the symbol for sodium. There's no N, there's no A in the word sodium. Where does that come from? It comes from the Latin name. So the Latin name for sodium is natrium. So a lot of these elements were discovered when Latin was the primary scientific language. And so they were given Latin names, and the symbols come from that. So sodium from natrium, potassium has the symbol K because its name is kalium. So lead, Pb is because its Latin name is plumum. From we get the word plumbing. Gold is Au from aurum, A-U-R-U-M. Silver is argentum with the A-G. Copper, you say, well, I understand the C. Why is it U? Cuprum, C-U-P. Yeah. Iron is ferrum. Ferrum. So yeah, there's Latin, occasional Greek names, but they're mostly Latin names. So all of those really weird ones, there is a reason behind them. And so, some of us really like to know what the reason is, and others are like, don't bother me with extraneous material. Really?
Yeah.
Oh, man. No, I love questions like that. Okay, so isotopes. All atoms of a given element have the same number of protons, but some of them have different numbers of neutrons. And so this is why that second tenet of the atomic theory, we have to change it a smidge, because not all atoms of the same element have the same mass. If they have different numbers of neutrons, they're going to have slightly different masses. It's the number of protons that they always have the same. So when we have atoms that have same number of protons, they're part of the same element, but different numbers of neutrons, we call these isotopes. Iso is a prefix that means the same. I honestly don't know what tope means. I really should look that up, but I always forget. Isotopes. So we'll talk about neon as an example. Neon has 3 different isotopes. All neon atoms have 10 protons, but some of them have 10 neutrons, some have 11 neutrons, and some have 12 neutrons. Why? I don't know. Because they do. We go out, we study neon atoms, and that's what we find, right? So because they have different numbers of neutrons, they're going to have slightly different masses. Yes?
Will they all have the same electrical charge?
They would all have the same electrical charge. They would all be electrically neutral as atoms. So because they have the same number of protons, they will all have the same number of electrons. And they will behave in almost identical ways. The differences in properties between the different isotopes, very, very small. Very small. And for the most part, their properties are identical. What's interesting is that the relative amount of each isotope for a given element is roughly constant. So if you isolated a sample of celium, where does that come? Celium, would that be an element that you could make ceilings out of? Helium. A sample of helium, say from the air in this room or from the air in London or something, and you looked at how many of this isotope and this one there are, you'd find that the relationship, the distribution is almost constant. Very, very small differences. So we look at the percentage of each isotope, and we call that the natural abundance of the isotope. So we express it as a percentage. Another number we talk about is the mass number. So the mass number for an isotope is the number of protons plus the number of neutrons. Those are the massive particles in the atom. So the mass number is how many massive particles are there? Total number of protons and neutrons. So we can symbolize the different isotopes using a nuclear symbol like this, where X represents the chemical symbol from the periodic table. Z is the atomic number, the number of protons. A is the mass number, the total number of protons and neutrons. And so here are the 3 isotopes of neon. They're nuclear symbols. Now, if I wanted to know for this first one, how many neutrons does it have? Well, I would just take the mass number and subtract the atomic number. The mass number minus the number of protons, that one has 10 neutrons. I'll do the same over here, 11 neutrons and 12 neutrons. They all have the same mass number. Another way to represent them, which is a lot easier to type into a computer, is using the element symbol. I'll get to you in just a minute. The element symbol and a dash followed by the mass number. You got a question?
Yeah. So I was taking notes on that last slide.
Mm-hmm.
What did you say about subtracting? You said the atomic number from the mass number.
Yeah. So I remember having a hard time keeping straight which number goes on top. Is it the number of protons or is it the mass number? And so what makes sense to me is these are stacked up so that you could subtract them. So 20 minus 10 is 10, and when you do that subtraction, it gives you the number of neutrons. So that's just one of the many little tricks that I keep in my brain to remember stuff. So we can also represent those same three elements, isotopes, as Ne20, or you could use the full name, neon 20, neon 21, neon 22. This way of notating them does not include the atomic number. But really, we don't need the atomic number, because if we want to know what that is, we've got a periodic table. And you just can't do chemistry without a periodic table. We used to have little credit card sized ones that the ACS would give us and hand those out. Nobody wants those anymore, because all you have to do is get a free periodic table app on your cell phone, and you've got all of that stuff just anytime you want. So here's a table comparing those three different isotopes. So here are the symbols for those. So Ne22, neon 22, or you can symbolize it this way. They all have the same number of protons. They would all have the same number of electrons as well. The number of neutrons is different. This one's 10, this one's 11, this one's 12. And there's no great way to predict, well, how many isotopes does neon have? We just have to study nature and figure it out. There's no way to predict, well, this one has 3. Why doesn't it have 4? I don't know, it just doesn't. Here are the mass numbers, that's just the sum. 10 plus 10 is 20. And then here's the natural abundance as a percentage. So 90.48% of naturally occurring neon is this first isotope that has 10 protons, 10 neutrons. Only 0.27% is neon 21, 9.25% is neon 22. And these are just experimentally determined percentages. And again, that's not something you would memorize either. Any questions? Okay, so we should be able to answer questions like this. What are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? Well, let's answer those questions in order. What is the atomic number for carbon? 6. So here's carbon on the periodic table, and the number above it is 6. That's the atomic number, which is the number of protons. So the atomic number symbolized with a capital Z, Z is 6. The mass number. Mass number is how many protons plus the number of neutrons. Well, we just determined that this has 6 protons. How many neutrons does this isotope have? 7. The only way we know that is because it said so right here. Carbon isotope with 7 neutrons. So 6 plus 7 is 13. That's the mass number, symbolized by A. And then what's the symbol? Well, there are 2 different ways of giving a symbol for an isotope. This doesn't specify, so if this was a question on a lab, I would accept either way. So we can do the nuclear symbol, which is the element symbol, C, and as a subscript on the left, we put the atomic number, 6, and as a superscript on the left, we put the mass number, 13. Or we could say C-13, or if you wanted to, you could write it out, carbon 13. That's one isotope of carbon. Any questions? Here's another type of question. How many protons and neutrons are present in an atom of this? It's potassium 39. Well, how many protons does it have? 19. There's 2 ways you could find that. One is it's given right here, 19. The other thing you could do is you could look at the periodic table, and potassium's number 19, 19 protons. How many neutrons? 20. So if we take 39 minus 19 is 20. Any questions?